Today we're going to look at a really nice problem that came from a 1989 entrance exam for a certain Japanese university. So let's see the setup. So for a positive real number a, let's suppose that f of x satisfies the following integral equation. So f of x equals x times e to the minus x over a plus 1 over a plus 1 times the integral from 0 to a of f of t dt. Okay, and our first thing that we want to do is determine the value of this integral from 0 to a of f of t dt. And we'll determine this in terms of a. But I'd like to notice that before we even get started, let's observe that this integral right here is, well, it's just a number. And, well, what does that really mean? Well, that means that this second part, which says find the maximum and minimum of f of x in some conditions, only depends on this first bit, this x times e to the x over a, minus x over a. But anyway, let's do this first part first. So what we'll do is take this entire equation and integrate it from 0 to a. So that'll leave the left-hand side of the equation equal to the integral from 0 to a of f of x dx. And then here we'll have the integral from 0 to a of x times e to the minus x over a dx. And then here we'll have 1 over a plus 1. Here we're using the linearity. And then a double integral, both with respect to a, of f of t dt and then dx. Okay, but now let's observe over here that this integral from 0 to a of f of t dt is just a constant, just like it was before. So that means, in fact, we can factor it out of this trivial integral from 0 to a of f of x dx. And that means this term right here becomes a over a plus 1 times the integral from 0 to a of, let's see, f of t dt. Okay, so that's what's happening with that term. Notice the a in the numerator came from that integral from 0 to a of dx. And then, well, let's do just a change of dummy variables inside of this integral to make it match with what we have over there. And now that'll be the integral of f of t dt. But now this next bit, this part that I may be underlining in red, can be done with the di method. In other words, with integration by parts. So let's set that up. So we've got our derivative column and our antiderivative column. We'll put, let's see, x here and e to the minus x over a here. We do that because we want the differentiation column to become easier when we take the derivatives. And x becomes a simpler function when you take its derivative. In fact, that's true about all polynomials, but that's just a good rule of thumb when you're setting up your integration by parts. Okay, so taking derivatives, we have 1 and 0. Taking antiderivatives here, we'll have minus a times x to the minus, e to the minus x over a. And then a squared times e to the minus x over a. And then, of course, what we need to do now is match everything on the diagonal and then alternate the sign. That's just our quick way of doing an integration by parts. Okay, so let's see. That's going to give us minus a times x times e to the minus x over a, where this minus sign attached to the a just got covered up by an arrow, but it is there. And then minus a squared times x, I keep doing that, e to the minus x over a. And then we need to evaluate that from x equals 0 to x equals a. But I don't like this hanging minus sign, so what I'll do is I'll change these minus signs to plus signs and then make my evaluation from a up to 0. Okay, so let's see where that leaves us. So plugging in 0 will simply give us a squared. I think that's pretty clear. Minus, what do we get if we plug in a? Well, we're going to have a squared for this term. And then we'll have e to the minus 1. And then here we'll have another a squared times e to the minus 1. So we might as well add those together and get 2a squared times e to the minus 1. And then, well, let's go ahead and bring this down. So we have a over a plus 1, and then the integral from 0 to a of f of t dt. But what do we have here? Well, now we've got an equation that we can use to solve for our integral. So let's maybe subtract this a over a plus 1 from the right to the left-hand side of the equation, just keeping in mind that we'll take this coefficient of 1 here to be a plus 1 over a plus 1, meaning that when we do that subtraction, we get some simplification. In fact, we'll have 1 over a plus 1 times the integral from 0 to a of f of t dt. And of course, that's after we subtracted this over. But from there, all we have to do is multiply by a plus 1, and we have the integral from 0 to a of f of t dt is equal to, well, let's write this as a squared times a plus 1 times 1 minus 2 over e, when all is said and done. Okay, great. So we've taken care of this first bit. Now let's do the second bit. So using the result of this first bit, which we calculated before, our function is now equal to x times e to the minus x over a plus this constant. And this constant, well, it depends on a, but a is a parameter here. You can think of it as a fixed parameter. And we've got a squared times 1 minus 2 over e. And now our goal is to find the maximum and the minimum of our function if our parameter a is between 0 and 1, and we have x on the closed interval from minus 1 to 1. Well, that motivates us to use the extreme value theorem because we have a continuous function on a closed interval. And so that means we need to find the critical points and then evaluate our function at the critical points and the endpoints, pick out the largest and the smallest. So let's find our critical point now. Okay, so in order to find the critical points, we need the derivative of our function. Remember, the critical points are where the derivative is 0 or does not exist. The derivative will exist everywhere for this function, so we just need to know where the derivative is 0. Now, using the product rule, that's going to give us e to the minus x over a. And then let's see, minus x over a times e to the minus x over a. I'm going to maybe factor an e to the minus x over a out of the whole thing. That'll leave me with a minus x. So what does that tell us? That tells us that if x equals a, that is a critical point. And well, that's because that's where this derivative will be equal to 0. Okay, well now we need to look at f evaluated at minus 1, f evaluated at a, and f evaluated at 1 to determine which one is the biggest and which one is the smallest. So let's see, f evaluated at a minus 1 will be equal to minus e to the x over a, to the 1 over a plus a constant. And I'll maybe just use the letter c for that constant. Notice that constant will be the same for all of these functions, and so, or for all of these evaluations. That means it won't really have anything to do with which one is the largest and the smallest. This other bit will. Okay, and then if we evaluate this at a, what do we get? Well, we're going to have a times e to the minus 1 plus, well, that same constant. And then finally, for f of 1, we'll have e to the minus 1 over a, and then, well, of course, plus that same constant. Well, now notice we know that a is positive, so that means we've got a positive number plus a constant, a positive number plus the same constant for these last two, but here we've got a negative number plus a constant. Well, that means that, well, this is most definitely our minimum. And, well, what is that minimum value? Well, it's going to be e to the minus 1 over a plus that number right there. And now determining which one of these is larger is a little bit tricky, But what we can do is use the first derivative test. So let's notice that this first derivative is positive if x is to the left of a, and it's negative if x is to the right of a. That means this function is decreasing between x equals a and x equals 1. But if it's decreasing between x equals a and x equals 1, that means that f equals, or f of a has to be bigger than f of 1. So putting that all together, that tells us that this is in fact our maximum value for our function. And there you have it. So we've done everything here. We evaluated our integral, and then we determined the extreme values of our function. And that's a good place to stop.